Hello and welcome to today's class. Let's look at the second law of electrostatics. Last class we dealt with the first law of electrostatics. So let's look at the second law of electrostatics called the Coulomb's law. So Coulomb's law states that the force of attraction between two charges is proportional to the product of the charges and inversely to the square of the distance apart. That's how you state Coulomb's law. So I'm saying this, please. I said Coulomb's law states that the force of attraction F between the two charges. So let's say I have charge 1. So I have a charge 1. Let's say Q1 as charge 1, Q2 as charge 2. Distance from here to this point here is called R. So R is called distance. So I'm saying that the force of attraction between these two charges, Q1 and Q2, is that proportional to the product of the charges. So I'm saying that F is that proportional to what? The product of the charges. That's Q1 times Q2 and inversely to the square of this is apart. So I'm saying that this force again is inversely 1 over the square of the distance apart. So that's what? R squared. These two are from Coulomb's law. Combine it together, I'm saying that this F is directly proportional to what? Q1 times Q2 give Q1 Q2, right? Then inverse proportional to what? 1 over R squared. I have this. Combine Q1 Q2 with 1, I'll have that F is equal to F, also that the force of attraction is equal to Q1 times Q times 1. That gives Q1 Q2 all over what there? R squared. So R squared. I have this. If I have this symbol in mathematics, to take up this symbol, I'll introduce what there? A constant. That's K. So I'm saying that F equal to a constant. So F now is equal to K Q1 Q2 all over R squared. This law is from Coulomb's law. So F equal to K Q1 Q2 over R squared is from the concept of Coulomb's law, right? So that's basically Coulomb's law. So this formula is the Coulomb's law formula. All right, I have this. All right, I have this, please. Now, here's the concept, please. Let's get the exact value of K. So I'm saying that this K here, K is equal to 1 over 4 pi E naught. We said K is a constant, and K being a constant is expressed as 1 over 4 pi E naught. What is equal to 9 times 10 to the power 9 Newton meter squared per Coulomb squared. Bear in mind that K is given as 9 times 10 to the power 9 Newton meter squared per Coulomb squared. So I have this value here. So bear in mind that this top here, E naught, is called the permissivity of free space. Permittivity of free space. That's the value for E naught. That's the name of E naught. That's the meaning of E naught. E naught means permissivity of free space. That's basically E naught. So I have this, please. So here's the concept, please. If K is 1 over 4 pi E naught, it means that my force of attraction F can also be expressed as what's K? We said K alone gives you this. That's 1 over 4 pi E naught. This value is for K. Then bring this up, so times Q1 Q2 all over R squared. Combine it together, so it means that I can express force of attraction as being equal to 1 times Q1 Q2 give Q1 Q2 all over 4 pi E naught R squared. So I have 4 pi E naught R squared. So I can express force of attraction as being equal to KQ1 Q2 over R squared or Q1 Q2 all over 4 pi E naught R squared. This is like the concept behind Coulomb's law. The force of attraction between two charges is proportional to the product of the charges and inversely the square of their distance apart. So I have this basic derivation for Coulomb's law. Please, let's look at how can we express Coulomb's law in terms of vectorial form. That's where we're going, please. So Coulomb's law in terms of vectorial form, please. Coulomb's law normally is F equal to KQ1 Q2 over R squared. But in terms of vectorial form, for vectorial form or vector form, right? Coulomb's law can be expressed as F12 resultant F12 is equal to KQ1 Q2 all over R12 magnitude all squared dot unit vector of R12. This is how you express Coulomb's law in vectorial form, right? F12 equal to KQ1 Q2 all over R12 magnitude all squared 1 over unit vector of R12. This is how you represent Coulomb's law in vectorial form. Of course, they are similar. F, K, Q1, Q2. Just observe the difference, right? Unit vector and magnitude squared, right? That's basically how you express Coulomb's law in vectorial form. All right. We're looking at several cases when it comes to Coulomb's law in vectorial form. We're looking at the concept of linear charge configuration, triangular charge configuration, rectangular charge configuration, square charge configuration, and semicircular charge configuration. Let's start with the linear charge configuration under the concept of Coulomb's law in vectorial form. Let's look at the linear charge configuration. Let's discuss the linear charge configuration.